So we are very happy to have Alireza here. He got his PhD. He did his PhD at Simon Fraser University with the other Bogosian,
yeah.
And then he moved to the Institute for the Air Universe in Korea, South Korea. And then he loved Canada so much that he came back to Canada. Now he's a postdoc at UBC. And he's going to tell us about big lens and everybody else that he can do.
Yeah, well, thanks, Amir. Yeah, it's nice visiting, and thanks for being here. So I wanted to talk about some recent work we've been doing on cross-correlating weak lensing and thermal SC effect, and what we learn about ICM gastrophysics, and what are the implications for galaxy-galaxy lensing measurements. So it's a work done mainly with this group of people, and my talk is mostly based on these papers. So what's thermal SC and why we're interested in it? So thermal SC is a secondary effect and happens when CMB photons go through regions where there is hot ionized particles. And by scattering off these hot particles, they gain energy so that their black body spectrum is getting distorted. And one can compute how this distortion happens, and you have such a spectral distortion with respect to black body spectrum so that you have some decrement and below 217 gigahertz and some increment above 217 gigahertz, so that the temperature change would be this spectral function times an amplitude, which is effectively it depends on the number of ionized particles you have on the way and how hot they are. So the quantity of interest is this comptonization parameter, which is effectively an integral along the line of sight of temperature-weighted density of these ionized particles. And it is interesting because we can study the distribution of baryons in the sky from this probe, and even when the density of these baryons is relatively low. So why we're interested in baryons? Because there are a lot of things we don't know about the baryonic processes on the astrophysical scales. And for example, from CMB, on one hand, we know how much baryons we should have in the universe. But on the other hand, only a small fraction of these baryons are in the form of compact objects or are hot enough to be observed by X-ray measurements. And a big portion of these baryons are observationally missing. And in that sense, thermal SC is a redshift-independent effect with a unique signature. And it's probing interesting time in growth of structure history. So it would be a useful probe for us. And why we want to cross-correlate it with gravitational lensing? Well, lensing is a good measure of mass along the line of sight. So by cross-correlating these two, you're practically picking the regions where there is mass and there are baryons. And because the lensing surveys usually have a narrow kernel in redshift, then you are exploring this relationship between gas and between mass in a narrow range in the redshift, and you are automatically saved from higher redshift or lower redshift contaminations to the TSC signal. So that's the idea, and as you probably know, such a cross-correlation has been done before, where TSC maps constructed from Planck maps are cross-correlated with CFHT mass maps. So that through ILC techniques, by combining the Planck maps, you can remove the primary CMB and other contaminations, and the final product would be a set of maps that with different cleaning strategies that then you can use to detect your signal, do all kinds of cross checks and null tests and everything. So the lensing part is coming from the mass map from CFHD, which is, or the convergence map, which is effectively an integral along line of sight of density contrast with a window function, the lensing kernel function, which for CFHD is peaking around 0.4, and it's this narrow region here. And that's the advantage of cross-correlating with lensing, with low redshift lensing, because then you are exploring this gas and mass relationship in this narrow, localized redshift range. So the result of this cross-correlation study are presented in terms of correlation functions over a wide range of angular scales, and for cross-correlating with different TSC maps that were constructed. And so the takeaway here, what we're supposed to get from here, is that first of all, there is a relatively significant detection here, and that the variation you would expect in the signal from different constructed maps is smaller than what you would have if your maps were contaminated significantly. You're also, and this plus and some other plus in the paper are also supposed to convince you that your signal is robust, you don't have contamination, and null tests are good. And also finally, that what you predict like from theory, which is this solid line here, and it has nothing, it's not a fit to data, it's just your prediction from your theory. It agrees relatively well in terms of amplitude and shape to what you detect. So it's all good.
So these are 4 different patches?
No, these are cross-correlation with different constructed maps. So each of them have a different cleaning and modeling. And as I said, so the variation is not big, so it's good. So it's good, but it's not the complete story, because in this prediction, what you have a simple bias model. The bias between gas and mass is constant. But on the other hand, this is not a stacking process. This is a large scale cross correlation of everything with everything in the maps. So, and the simple model doesn't tell you exactly how much of signal is coming from where or from what objects. And then you can go further, and so with this model, the combination you could constrain is a bias times the temperature of the gas in your model and the density of the gas. But the question is, could you do better? Can you get some more information about where the signal is coming from, or about your understanding of the gas model? Or in other words, how your modeling of the gas could predict this signal. So in that sense, you could go further. You can do a halo model analysis. In the halo model, your cross-power spectrum is coming from 1 halo term and 2 halo term, and you're assuming everything is in halos. So that gives you the whole power spectrum. And what you need basically is your modeling of the density in terms of like the Fourier transform of your density, and your Fourier transform of your understanding of baryons or pressure profile. So, and basically your modeling of the pressure would be what you're interested, and you want to know how what you get from this halo model is going to contribute, is going to compare to your data. Yeah.
Sorry, so I thought that this was what was in the theoretical curve in the previous one.
No. Okay, in this you only assume that your gas power spectrum has a constant bias with respect to your matter power spectrum. And it doesn't have any mass dependence on, like it doesn't depend on the halo mass. It doesn't depend on anything. It's just a constant bias between matter and gas. But here in the halo model, yeah, but nonlinear to go further. But here, your pressure profile depends on the distance from halo, the mass of halo, and redshift. So you put all these together, and then, you, for example, you can get a 1 halo term, and similar way a 2 halo term. And then you can predict by putting different models of pressure here. So this is what you get.
So can I go back to that?
Sure.
B gas. What is actually the definition of B gas? Is it delta N gas over N gas or delta B gas over B gas?
Here,
Well,
or in the previous one?
You gave it, well, one of the co-authors is here. He must know.
Yes, Norman should know, but.
What is the answer? B gas equals.
Should I answer, or you want? Well, if you mean this, this one, it's between power spectrum of gas and matter.
Well, what aspect of gas? Is it the density or the pressure?
Yeah, density.
So, and yet, the thing that you're using is pressure.
Yeah.
So why isn't it a pressure bias?
No, it's. I didn't say it's a pressure bias.
You said it was a density bias.
Yes.
So how,
He's asking why didn't we use a
why,
pressure
why
bias?
isn't it a pressure bias? Why is it a density bias?
Well, you just assume that gas is just following matter with the.
Pressure.
That is isothermal, right?
But so your temperature, you assume the temperature is, your description of temperature is like, it's gonna scale like 1/1 plus redshift. And so today you have a temperature that you're gonna fix, and you assume your temperature is just changing like 1/1 plus
I
redshift.
think they thought it was the right thing to do. I think they was just the simplest thing to do.
Yeah, it's the simplest thing. That's why I'm saying it provides effectively.
Just to say,
Sure.
pressure will have a completely different bias than gas does. Yes.
Yeah.
wasn't supposed to be some great do that.
Well, no, but I know, but it's got a formula here.
Yeah.
2.01 plus or minus 0.31.
Yeah,
And
Yeah.
yet, you know,
Well, it's what you get from that model, but how elegant that model is a separate story. Yeah, but so that's why we went further. That's why we wanted to look at different things. So from a halo model, you have predictions. So what we have here are two sets of plots. The solid lines are the prediction with the Planck best fit parameters. These are not the new parameters. These are 2013-14 parameters. And also with the WMAP7 best fit cosmology. And we have two pressure profile models. And so the idea here is that, the takeaway here is that, first of all, cosmology is very important on all scales. And some pressure profiles that are fitting the stacking studies very well do not necessarily work well over this long, large angular scale, and for all the objects that could cross-correlate here. And so in terms of a comparison with data, then what you can take is the model which fits better to your data and try to work with that. So in that case, what was the best model was a Planck cosmology with this isothermal beta model. And
So the beta model is again a model for density, right?
yeah, and temperature. It has both.
Right, but it assumes the temperature is isothermal in the
Yes, exactly, yeah.
But we know clusters are nowhere near as
Yeah, that's the
on
point.
scales that SC matters, right?
Yes, that's the point.
but you use the universal pressure profile so they do have the pressure modeling. Yeah.
Okay, and that's, so right, so that's the
So the solid plot red one is the
pinkish
plot
curve.
one.
Where is
So-
the pinkish?
Well, it's red. It's that.
So-
it goes up to
Oh,
3.5 by 10 to the minus 9. So it over predicts.
Yeah, forget the blue lines, they don't have anything to do with anything. The red lines.
Yeah.
That's Komatsu and Solja?
Yeah.
Yeah. But so the point is, we were not going to, we just wanted to see what Halo model predicts and which one is getting a better agreement with data. That was the point. Okay. And it seems like with this description, this statistical description of cross-correlating everything with everything, this isothermal beta model with the Planck cosmology was fitting best. That was the idea. But then what you can do is to see how much of the signal is coming from where and from what. So what was done was to break this signal into different bins, into the contribution from low mass halos, high mass halo, and inside virial radius, and like beyond virial radius. So this is a breakdown of the signal into these components based on this model, based on this best fit model at the time at least. So the results which were interesting at least at the time, or like not unexpected, was that a big contribution of the signal is from beyond virial radius. And also low mass halos have a significant contribution, at least in the framework of halo model with this best fit model, with this best fit pressure profile. And then you can, of course, use the model and then work out what temperature for the gas you get from that model. And the numbers you get are kind of hinting towards a gas, a plasma, which is not necessarily hot enough to be observed by X-rays. So that was at least interesting at the time. So if you want to summarize the things we got from here and the questions that raised, so here's the summary. As I said, the interesting at the time was that we have a considerable signal from low mass halos, at least with this model, and a contribution from beyond virial radius. And also that there is not necessarily a pressure profile which could predict this signal over a wide range of scales and masses. And and cosmology is important, especially sigma 8, omega m, could have a big effect. But on the other hand, there are some inherent shortcomings with halo model. Like describing the gas beyond virial radius through this framework is not necessarily a very good idea. Or you could have other objects which could contribute to your signal, like filaments, but you don't have them in the halo model. So they would contribute to your signal, but you don't have necessarily a good description of that in your halo model. And also that baryon feedback, we know distribution of gases are important. That's where the signal is coming from. And then the question is how much impact the baryon feedback could have on this signal. Or is data sensitive enough so that you can use this to have a feedback on or understanding of baryon feedback? So these were the questions and ambiguities we were dealing with at the time. So just a couple of plots in terms of elaborating more on this. You've probably seen plots like this, where the ratio of the power when you have baryon feedbacks to the ratio to the power when you have like only dark matter for different feedback models. I'm going to talk about it. Is plotted for different feedback models or at different redshifts. And then the takeaway here is that for a wide range of scales of interest, baryon feedback could have a significant impact on the power. And if we're doing, say, lensing measurement on these scales, we have to consider the impact of baryons here. And also people have looked, different people, like groups have looked at a pressure profile which could describe the gas on a wide range of masses. So an example is here. It's relatively recent from Al's simulation. I'm going to talk about that. So what we have here is different mass bins, cluster mass bins. And this is the tail of this plot. I just put it here. On this range of distances, and this is the pressure profile. So we get from low mass to high mass. And these data points are what you get from the simulations. And these curves are from different profiles. So blue line is from a universal pressure profile, and the rest are GNFW where you treat the parameters of the model differently. And these panels just show the ratio, the difference. And the takeaway here is that there's not necessarily a pressure profile which could describe what we have in a wide range of masses. So you should.
Where is R200 on there?
Sorry.
Where is R200 on these plots? Oh.
So it's R500 here.
Okay.
And then you should go beyond that here somewhere. Yeah. So going back to, yeah. So going back to the questions and ambiguities we had, what we can do is to look at simulations, see what different simulations tell us and what we can learn about each of these. Then we can test the Halo model predictions based on that. So what we did, we used this OWL simulations. It stands for our Vermigny large simulations. And the good thing is that they have a wide range of baryon feedback in their simulations. So you have a no-cool case where there's no cooling and star formation processes in there. But then you can add these cooling processes in this ref model. And you can also add different AGN feedback models, different AGN, like AGN with different power. Like it depends on how hot this AGN feedback is. But then, so you have this wide range of baryon feedback that you could use to study their impact on your TSC signal. And so just so you see, these are Y maps from this simulation for different feedback models with the Planck cosmology, Planck 14, not the new one. And for a comparison, you have what you get from a WMAP7 cosmology for the same model. So this AGN8 is going to be your fiducial model because overall it fits all the data better than others. But then we want to see how others do as well. So with this simulation, we have Y maps. We can produce convergence maps, and we can cross-correlate.
So just give me a sense of what remind me what AGN 8.0 is. What does that mean?
So it's a so the black hole has pushes radiation outside, and it somehow represents the temperature of this wave of heat which comes out from the black hole.
So it's like an periodic AGN bomb.
Yeah, yeah, something like that. But effectively, what it does is that it pushes the gas to further distances. So the more violent it is, it pushes the gas more to larger distances.
What's it tied to?
Sorry?
How are the AGNs defined?
Well, I can show you the details.
Blondie,
Well, no, it's not that short distance. Because the simulations are larger. The question is, how are you identifying where the AGNs are? That is to say, where the feedback is occurring and how its efficiency goes with the mass.
Oh, that I don't know. I should ask the one who did it.
But in the halos, full halos, because as you know, we tied it to star formation based upon guidance.
Yes, exactly.
Tying it to the halos, which I thought was a good idea at the time, turned out not to be very good.
Yes, I agree, but they did it anyway.
They did it.
And then the numbers, if I recall correctly, but don't quote me, this is, they hang on to the energy until they can calculate how much it'll heat the gas to, and then they let it off as well. And that's what the 8.5 8.7.
Over some scale.
Yeah, and I forget how they cut the scale for it.
So the energy efficiency is the same in all three, right? It's
I
just how long you
believe,
wait.
I believe that's right, but they just wait longer. Exactly.
Yeah, I think so. That's my understanding, but I should double check. But for our purpose, we use these maps, and we have the corresponding convergence maps. So we cross-correlate in the same way that data was treated. the actual data. So this is what you get. Here we have a WMAP7 cosmology, a Planck cosmology over the same range of angular scales. This red band is the data that was originally detected. And different lines here are corresponding to different feedback models from simulations. And there is this gray band, which is working as a, or uncertainty in this, you could have in these models just from sampling bias. So it's just kind of represents an error of our understanding in these simulations. So the takeaway here is that the simulations roughly agree, more or less, with what was detected. And that cosmologies, we knew it's important. Baryon feedback would be more relevant on smaller scales that we could guess. And there are, for example, non-trivial things, semi-trivial things you could guess or see from these plots. Let's say no cool is the one where you have gas, but there's no formalism for that to cool down. So you have a lot of gas here, hot gas that cannot cool down. So you have a lot of power on the small scales. On the other side, you have the most violent AGN, which pushes the gas outside. So you have less power in the small radii, but then you have an extra power on larger distances.
So if I'm reading this right, there's actually kind of no agreement at past 15 or 20.
So
with any of the models, right?
yeah. So first of all, it's a correlation function. So all these points are correlated significantly first. And so the larger scale, so it is a real space cross correlation. So larger scales might not be good representative here. But what I want to say is that you don't have a significant discrepancy here. It's just all real space correlation function.
Is this all done within a single box simulation?
No, it's like, it's a light cone, and we have 10 line of sights.
And what cuts were you?
For what?
Presumably you didn't want to have the things that are really nearby.
No, yeah.
Cuts were you?
So here we didn't do any major cuts. We have cuts, redshift cuts and everything, but here nothing. Whatever you could see in the sky was done up to very, very nearby.
So did you actually try and mimic what was done with the data by the simulation?
Yes, and so these simulations.
History shows
Yeah.
that fluctuation on the larger angular scales can be very large.
That's right.
Because of what's just coming into the line of sight and what isn't.
Yeah, they were taken care of. So you make sure you don't have anything very nearby, right in your face. And then.
And that was done with the data as well.
Yeah, I assume.
Well, I don't think you can assume.
No, I mean, I didn't do the data. I didn't do the data, but I assume they did it because.
Well, no, they didn't just use the Y
We
map.
just used the
of
Y map
Planck.
straight up.
Oh, with the Y map.
So it's whatever is in that direction, which we don't actually know.
That's right. The point is that when you cross-correlated the lensing, anything very nearby would not correlate, first of all, but this Y map, right? I believe they did. I don't know the details
Okay, so
of how exactly those TSC maps were made.
what you're saying is that the redshift dependence
Yeah.
of lensing cuts out nearby things.
Nearby contamination, it cuts out, yes. Like anything from galaxy.
Nearby signal in psi, y, kappa.
Well, he showed that.
Yeah.
It's not contamination, it's reality. But the question is, because fluctuations can build up enormously, but it may be that you're right, that the effective selection function of the lensing punches out a redshift range that, I mean, the thing is, when we did the X-ray
Yeah.
essay, attempt at cross-correlation,
Yeah.
a lot of those X-ray sources, the clusters are nearby. I mean, fairly nearby, right? And here, I think that what you're telling me is that you were selecting against things which are essentially less than redshift, about 0.1 or so. And maybe
Yeah, and so it's 0.1 to point.
That's what those red lines are.
Yeah, exactly. Yeah.
So that would not include effectively objects that are less than redshift, about 0.1 or maybe
Because there's no
0.5.
power of lens. Exactly.
Yeah.
No, so that's.
But it's also a bit odd, and this I don't understand, which is, what do you do the cap on that? They don't have any, they don't have power out to not even the size of their image, right? To CFHD lenses.
Well, that's the other aspect.
So that's the law.
They've got an
I don't
effective,
trust.
they've got an
Yeah.
effective filter
Exactly.
associated with the lensing
And it's not
that
obvious.
has to be pulled
And
in.
it's not obvious to me what that filter is.
And if you're comparing with simulations, you have to pull that in.
Yeah, so that's why
So
I'm
we had a
saying,
discussion, a fairly deep discussion about it.
yeah, so that's why, but this is gonna be fixed.
Your heated discussion now.
But the good thing is that, say with RCS2, this problem on these scales is fixed. You have much larger fields. You have a better control on these larger modes. And if you do a real space analysis on these scales, you're having a more accurate results. That problem is practically fixed.
Just remind me what L is like 20 arc minutes.
I think the best thing to look at is this one. It doesn't have L. Wait.
But that does show, here, go back to what I was saying. There. So it doesn't cut off really well. Right? If you go down to power of a half or whatever, right?
Yeah.
It's you know, 10.
Well, no, but yeah, no, 0.5 is, I mean, so once you're down to that 0.1, it looks like it's dropped enormously.
Well,
yeah,
I would
kind
say
of.
by a factor 2.
Mm,
Yeah.
No,
Yeah.
That's where most X-ray selective clusters are.
Yeah.
All the way in the end.
Yeah. So you gotta work.
Yeah. You have to really model this stuff carefully.
So, okay, so if I want to, so this is what we got, but more interesting for us was the small scales when baryon feedback is more important. And this is like Planck resolution that we did a large scale correlation. But you want to go to smaller scales when you have a high resolution map. And the point is that if you go to, it's the same correlation function, but on much smaller scales, practically accessible by lensing surveys, but not with Planck. ACT could do it, or SPT. And the point here, I have a WMAP 7 plots for different feedback models with dashed lines. And I have 2 models for Planck cosmology. And again, the takeaway here is that cosmology is very important on small scales, and baryon feedback can potentially be constrained if you have a high resolution SC map. But what was more interesting for us at the time was some of these predictions from Halo model, that how much of the signal is coming from which objects and what distances. So here is a breakdown of the signal. So what we have again is the correlation function. This green one is the total signal you have. And then you removed masses of like clusters with some lower masses. And as you cut, you lose signal. So the point here is that most of the signal is coming from clusters which have the mass between 1 and 5, 10 to 14 solar mass. But the contribution from small mass halos is not necessarily ignorable. So you have some low mass contribution to the signal, and you can quantify it, at least compared to this data that we have. And you can also cut in radial beams. So here again, we have the total signal. If you keep the stuff only below 1 video radius, that's what you get. So a significant portion, according to this simulation, with this fiducial model for feedback, a significant portion is beyond video radius. according to this simulation.
So I'm a bit confused, right? So anything over 10 to the 14th solar mass, anything beyond the virial radius doesn't actually know what's happening with the AGN in the center.
Yeah, so it's not just the AGN. AGN is part of the whole thing.
Okay, so there's other feedback.
Yeah, and in general, you have a baryon distribution. How AGN is working on it is part of the story.
The other thing is that the AGN feedback is on through the entire period, which means it's actually most devastating effects are early.
Much later,
Yeah. So that's why you get an effect in the outer region. It's not an AGN in the center of a cluster. It's the history, the emerging history.
Yeah, so if you keep everything below 5 virial radius, you're almost getting all the signal. But there is a big contribution from virial radius to 5 virial radius, according to simulation.
And are you saying that this is mostly, I know you're saying that it's due to a combination of effects,
Yeah.
not just the feedback. But do you have I mean, you've obviously looked at the other models,
Yeah, well,
like the one with just no AGN feedback.
yeah, so if you don't have any AGN feedback, you have more power here on smaller scales because you have more gas.
Power that comes from outside the real radius.
Yeah, it changes. I have some numbers in the paper, but
A lot of that actually from the groups that are associated with the cluster.
yeah.
So that in fact, this is an average entity, but it includes, I mean, this is going to be a question which arises, so you better prepare for it, because I know what Ma says about this, and I don't think it's right. I don't think that there has been a demonstration that there is a large amount of diffuse hot gas from the aesthetic observations, because the resolution is such that you can't tell if it's associated with groups and small clusters that are in filaments, or whether it's actually distributed and diffuse. And so that's the critical issue, and to a certain extent, these tests aren't ready for being able to do that because the resolution is good.
So, well, resolution here is 10 to 12 solar mass for this simulation. 10 to 12 clusters with 10 to.
In the simulation, I meant in the data.
Oh yeah, okay.
So it's the inferences you can draw from the data, which are.
This is the point I was making with you before. It wasn't clear
Yeah.
from reading the papers that Alireza is not claiming
Well,
Well, you sure did.
yes.
no. Here's the with the Halo model. The Neo Halo model is not going to have a good description of the gas beyond virial radius or the filaments or anything. It's just that your prediction from Halo model with the best fit is saying that. And part of the reason you have a discrepancy between other groups are saying about the contribution from beyond virial radius is that here, the numbers which are given here are from this beta model. It has a smoother transition to larger scales than a UP or any other profile, similar profile. So it's just obvious that you would have a more contribution from these larger scales by this model. But we knew.
Only because you didn't truncate it.
Truncated at what?
Well, in any of these models, you have to put a truncation radius on it so that it doesn't go off infinity.
Yes.
Because the curve of P R cubed rather than R squared R cubed just is.
Oh, there is truncation here. There is truncation at 5 virial radius on this.
That's already outside the virial shock.
Yes. Yeah, that's why I said you really want to look at simulations to address these issues because of that. But in terms of in terms of comparison to that Halo model, we have the same table here where you again beam the signal on low mass halos inside virial radius, low mass halos between 1 and 5 virial radius, and the same for the high mass. And then what you have is the contribution to the signal from this AGN model and the actual amount of baryons it corresponds to. Because whatever TSC signal you have is temperature weighted. You want to know how much of baryons it really corresponds to. And then you have a comparison to the halo model. So maybe the results the conclusions more or less hold, but there is a discrepancy between what halo model says and what the simulations say, for example. But some of the interesting thing is that, yes, the dominant signal is from high mass halos inside video radius, but they only correspond to a very small portion of the baryons. But because they're hot, they produce more TSC signal. And if you add these, they almost add up to 95% of the signal that is coming from here. But these baryons, if you add up, it's just about half of the baryons. So what it means is that the rest of them are beyond 5 video radius, and they practically don't produce any significant TSC signal. And this is this breakdown in terms of the correlation function. But that's the message here. At the same time of this paper, there was other study, Norman is here, which more or less predicted the same signal more or less the same comparison to data from a different set of simulations. And they have also feedback models. So this red one is more or less like the AGN, fiducial AGN we used. And this green is more or less like the no-cool model that's used in the other simulation. So the smaller scale and larger scale features are more or less agreeing. And this is what you get, more or less the same as what you have in the other paper. But so if I want to summarize this so far, yes, the idea is that there are a lot of baryons which are not hot enough to produce TSC signal, but they are way outside clusters. So baryon feedback is important, and what's important is that if you're doing smaller scale galaxy lensing, for example, this baryon feedback is not something you could ignore. And then the question is, can you actually use that to constrain the baryon feedback? So if you have a higher resolution TSC map, like ACT, SPT, then you can do much better in terms of the baryon feedback. And one other direction you could go is to work with higher order statistics of these maps. A lot of the scale dependence or properties of these could be explored better if you do higher order statistics. So I just show a few more plots to make these points here, and then I stop. So here is the same Y kappa correlation function we had for these different feedback models we had for different cosmology, but this is a zero lag correlation, so no separation. It's just like multiplying maps. So this is what we've been working with so far. But if you look at the other combinations, like Y kappa squared, again, it's zero lag correlation function. The idea is that you have a better discrimination between feedback models if you work with these. And there's another example where you have Y squared kappa. So you can find the combination. You can even go to higher orders, and you might have constraining power with upcoming lensing data, for example. But then the point is that you can pick the combinations which are good enough so that you can study these feedback models better. In terms of higher resolution TSC maps, so this is again from this OWL simulation. What we have is the TSC power spectrum for a WMAP7 and a Planck cosmology. And these are Planck data, ACT and SPT here. And these are the prediction from these different feedback models from the simulation. And the point, again, I want to make here is that if you go to smaller scales, your constraining power in terms of the feedback would be much better. Now, you can look at it in a different way. let's just focus on lensing. We don't even care about baryons now. This is a kappa Q, the same zero lag correlation function, but with low resolution. And as I said, you don't have like directly a contribution of baryons here. But you can go with the higher resolution maps. So this map is when you have this resolution here. And the point is that if you go to higher resolutions, the feedback can even have an impact on the lensing only variable, like quantities probe. So you want to, and this is already accessible by lensing surveys. It's just that you have to consider this effect here. For example, and it is another way of showing it. This is the same kappa Q quantity, but in a squished limit configuration. And again, the point is that if even for the lensing, you have to consider feedback, baryon feedback. It could make it could make a significant difference. And CFHT, for example, can already constrain this mildly. If you look at these plots, these are correlation functions. And so each box is a different feedback model. And each line here, it corresponds to the different masses of neutrinos. And again, it's a ratio of the correlation function to when you have dark matter only. So if you look at each line in each box, you are looking at different neutrino mass. And if you compare each line here, you are comparing the effect of feedback. So the point here is that CFHT data can already mildly prefer a combination of neutrino mass and feedback model, very mildly. So with, say, this, you could do much better. You can constrain these two degenerate effects on a smaller scales. So that's the focus now. So I think I'll just stop here. And yeah, thank you. Yeah.
So I was kind of questioning basically about the large angles.
Yeah.
So Ian asked about the disagreement between simulations.
Yeah.
And so I think he said something like, well, it was difficult to trust
Yeah.
the opposite. But isn't that the same part that causes you to conclude you have more signal coming from outside the real radio? I mean, isn't that the reason why the beta model fits better, for example?
No, so here, if you do a Fourier space analysis and then come back to real space, you don't have that problem because you have a control over Lowell contribution, which corresponds to these scales. So from Nick et al. Or this Yinje Ma study, when you do it from a halo model, you don't have that problem. But in terms of working with real data, there are advantages to work in real space. But then you don't have a good control over large scales because of that. But it will be solved if you have a larger survey, which is ready now. So you can fix that problem already. Yeah.
You compared with the C and D lensing cross SE?
This is the work. Yeah. We didn't, but we will do.
Okay.
Yeah, but no, for this work we didn't.
I guess there's some discrepancy in the two groups not really.
That was a story that was kind of resolved after, like in this latest work, where there was a discrepancy in the conventions between lensing community and CMB in terms of what they mean by resolution. But after that was fixed, the results are more or less agreeing. The difference would be, so the remaining differences are like in terms of the details of simulation or the pressure profile you use or the way you treat it, like in terms of real space or Fourier space. But that main thing was this disagreement of conventions, which is fixed.
Do you know
I can tell you. Yeah, so So this lensing, this smoothing kernel in CMB, they use FWHM as the lensing, as the resolution of this kernel used. But in lensing, they don't use FWHM. They use another combination. So these numbers don't agree exactly. But then it was fixed.
So it was the beam scale?
Yeah. It was, yeah. When we wanted to submit this with the other group, Norm et al., like Nick et al., then we realized that's the case.
I see. Okay.
Yeah.
That was part of that.
Part of the, yeah. Right.
And so it was a mistake in transferal?
No.
No, it was Ludo's use of the. First of all, it's not great because they're just using a Gaussian. I mean, it'd be much better if Ludo uses it. Ludo didn't have access. So he read the quote of, it's mean is whatever it is. And he thought it meant sigma not full half max.
Wow.
And that was what the origin of that was.
And that actually, I mean, there was a difference between the two groups.
Right, well, that's why we tracked it down because
that was what it was?
well, that's not the only difference.
No, it's not the
Big
only.
single difference, yeah.
All right. So let's thank Alireza.
Thank you.